At EGB320, we have designed and built a TRL-3 prototype of an autonomous robotic system that can conduct mineral mapping and collection on the lunar surface. In order to meet the requirements for a successful prototype, our robot needs to consistently pick and move the orange samples to the yellow lander while avoiding green obstacles, as well as being able to lift blue rocks to check for a sample underneath. Our final robot design cost approximately $179 to build, and it's contained within a 15 by 15 centimeter box at the time of being deposited at the lander. It also weighs 574 grams. It is distributed over 4 subsystems: mobility, sample management, vision, and navigation. The vision system captures a continuous video feed using a Raspberry Pi camera and processes each frame to identify the relevant objects in view. It then outputs a list of range and bearings to each detected object to the navigation system. The navigation system then employs artificial potential fields to inform the desired actions for the mobility and sample management system. Mobility receives the navigation commands and converts it into a PWM signal for the motors, while the sample management system opens, closes, and lifts the claw based on the commands sent by the navigation system.
The Rover has a specially designed mobility system that allows it to traverse the lunar terrain and the lander. It uses a dual motor controller to power the 150-to-1 geared motors. These motors drive wide but short profile wheels for increased grip and torque. The wheels are placed as close to the center of the robot as possible to allow the robot to spin on the spot for increased agility. The motors are able to move the robot very slowly, around 3 centimeters per second. We added skirts on the rear of the Rover to stop the back wheel from becoming lodged in the sample deposit hole. The overall chassis was designed to be low to the ground and balanced. In the software, we implemented a gradual movement system to decrease jerk and current peaks. This is done by setting a target movement speed and turn, and gradually increasing or decreasing from the current speed to the target speed.
My name is Akanksha, and I designed the sample collection system for this rover. This subsystem uses a gripper which consisted of a base plate and 2 geared claws with prongs on each side for rock lifting. Servo motors were used in this design as they were able to provide enough torque for the required opening, closing, lowering, and lifting motions of the claw. Foam was also glued to the insides of each claw as it provided a greater grip on the sample and prevented it from dropping. A micro switch was also included for robustness as it allowed the navigation system to know whether or not the sample had been collected. To program the servos, angles were calibrated for each motion and the corresponding PWM signals were called. Finally, the Pi GPIO library was used to prevent the claw from jittering.
For the vision system, we've used the illumination invariant HSV color space to threshold the different colors of each object. Morphological transformations such as erosion and dilation are further applied to reduce any noise in the image. A binary mask is then generated for each type of object, as shown on the frames on the right, from which the contours can be extracted and displayed, as shown on the left. In addition, the vision system was able to calculate the ranges and bearings for all objects in the field of view. Bearing was calculated by relating the horizontal field of view of the camera with the horizontal pixel displacement of the object. To calculate the range, we measured how the pixel distance from the bottom of the object to the bottom of the camera frame changed as the object was placed further away. We could then graph this relationship in Excel to obtain an equation that relates the pixels we measure on the screen to a real-life distance value.
The navigation subsystem is the brains of the robot, interfacing with all 3 other subsystems. It uses a state machine combined with information from the vision system and claw switch to determine what commands to give the mobility and sample management systems. Navigation towards a target whilst avoiding obstacles was achieved by implementing artificial potential fields. In this approach, the robot experiences an attractive force towards a target, such as a sample, and a repulsive force from each obstacle. An important feature of our robot is that it can detect whether it has failed to flip a rock and reveal a sample, and then try again. The relative locations of obstacles near the robot but out of view are stored in a map and updated by calculating how the robot has moved from the change in position of visible objects. This assists with navigating back to the lander once a sample has been collected. The integration of all these subsystems results in a robot that can successfully move off the lander, search for a sample and collect it, then return to the lander and deposit.